SwayamPrabha. Digital India. Educated India.
Good morning. Today I'll discuss on axial flow compressor. Contents of the lecture are two-dimensional pitch line design and analysis, work done factor, stage temperature rise, stage isentropic efficiency, and stage pressure rise. I'll be limited here to the discussion of two-dimensional pitch line design and analysis of axial flow compressors. The basic component of an axial flow compressor are the combination of rotor and the stator. Thus, a row of rotor blades followed by a row of stator blades is called a stage. The inlet guide vane IGV, which is a row of stator blade, is often provided ahead of the first stage of the compressor. Here I have indicated the picture of a multi-stage compressor of a real gas turbine engine, where you can appreciate the series of rotor blades of aerofoil constructions. The schematic of a high-pressure multi-stage axial flow compressor has been presented in the figure here, where one can appreciate that the rotor is connected to the hub while the stator is connected to the casing. Furthermore, the stage has been indicated here, which is a combination of the rotor and the stator. Here, a IGV is presented ahead of the first stage. Furthermore, I have drawn the central plane by a dotted line, which is a circumferential axisymmetric plane between the hub and the casing. One should note that there is a contraction of flow annulus from the low pressure to the high pressure end of the compressor, such that the axial velocity is maintained at a reasonably constant level despite of increase of density of air. In an axial flow compressor, the flow tends to be high while the pressure rise per stage is low, and it also maintains high efficiency. For an axial compressor of high hub to tip ratio, that is, if the blade height is considered small compared to the hub radius, then the radial variation in velocity and pressure may be neglected, and thus the performance of a compressor stage is calculated from the blading at the mean radial section, which is called the pitch line design. Now let us consider the flow through the compressor as compressible, and the velocity diagram is presented here. Here the velocity diagram of the compressor stage. So let us consider the mean circumferential section, and if we stretch that circumferential section on a plane of paper, we'll get series of blades. In this case, I have considered first the IGV followed by the rotor and then the stator. Thereby, the station 1 represents the exit from the IGV and inlet to the rotor, and thus the station 2 indicate the exit from the rotor and inlet to the following stator, and station 3 indicates the exit from the stator. As usual, Z be the axial direction and theta be the peripheral direction. Now, at station 1, I have drawn the velocity vector as W1 plus U1 is equal to C1. C1 makes an angle alpha 1 with the z-axis. Similarly, W1 makes an angle beta 1 with the z-axis. So thus alpha 1 is called absolute inlet air angle and beta 1 is the relative air angle at inlet. Similarly, if I draw the velocity triangle at exit of the rotor, it would be W2 plus U2 is equal to C2, and alpha 2 is the absolute angle at exit to the rotor, and similarly beta 2 is a relative angle exit to the rotor. Now look, beta m is the angle that vectorial mean velocity Wm makes with the z-axis, and thus d, which is the drag, will be parallel to vectorial mean velocity, and lift is the perpendicular to vectorial mean velocity Wm. So thus I have indicated here D and L is the drag and lift on the rotor, where U is the tangential velocity or the blade speed. Similarly, for the stator, here at station 3, C3 is the absolute velocity at exit from the stator, and alpha 3 is the angle that C3 makes with the z-axis. Now, I'm sure you have appreciated the velocity triangle of a stage, that is particularly the velocity triangle at inlet to the rotor and exit to the rotor. Now let us apply energy equation for compressible flow through a compressor rotor. Here I have referred the velocity triangle at inlet and exit of the rotor, as I have explained earlier. Now the stagnation enthalpy rise across the rotor row of the compressor stage can be obtained from the Euler equation, where the work input per unit mass flow or the specific work input can be expressed as W is equal to U into C theta 2 minus C theta 1. That's equal to U into W theta 1 minus W theta 2, where C theta is the tangential component of C and W theta being the tangential component of W, and U is the blade speed. Now from the steady flow energy equation applied between the station 1 or 2, which is valid for compressible irreversible flow, I can write 802 minus 801, that is enthalpy rise across the rotor, equal to U into W theta 1 minus W theta 2. Thus, Cp into T02 minus T01 is equal to U into Cz within bracket tan beta 1 minus tan beta 2. Now Cz is the axial component of velocity. Now this relation I can get from velocity triangle. Now please note that flow at the exit from the rotor would be deflected in the stator blade. However, there will be no work input in the stator. Therefore, the enthalpy increase across the stage would be Cp into del T0, where del T0 is the temperature rise across the stage, would be equal to Cp into T03 minus T01, that is equal to Cp into T02 minus T01, that is temperature rise across the rotor, is equal to U into Cz within bracket tan beta 1 minus tan beta 2. Thus, the stage loading is defined as I is equal to Cp into del T0 divided by U square, where del T0 be the total temperature rise across the stage. That is equal to Cz by U into tan beta 1 minus tan beta 2, equation number 3. Now, if the absolute velocity of air leaving the stage, that is C3, is made equal to C1, while alpha 3 is equal to alpha 1, then the increase in total temperature del T0 is same as that of the static temperature del Ts across the stage. Such a design is called the repeating stage. Thus, for a repeating stage, del T0 would be equal to del Ts, where del T0 is the total temperature rise across the stage and del Ts be the static temperature rise across the stage. And again, for the repeating stage, please remember C3 must be equal to C1 and alpha 3 is equal to alpha 1. Thus, for a repeating stage, I can write psi is equal to Cp into del T0 divided by U square is equal to Cp into del Ts by U square. That is equal to Cz by U, which is equal to 5 flow coefficient into tan beta 1 minus tan beta 2. Now from the velocity triangle, I can write phi is equal to Cz by U, that is equal to Cz divided by W theta 1 plus C theta 1, which yields 1 divided by tan beta 1 plus tan alpha 1, referring to the velocity triangle. This reduced to 1 by phi is equal to tan beta 1 plus tan alpha 1. Similarly, I can write phi is equal to Cz divided by W theta 2 plus C theta 2. This yields 1 by phi is equal to tan beta 2 plus tan alpha 2. Equation 4 now can be written as I is equal to 1 minus phi into tan beta 2 plus tan alpha 1. Cz by U is equal to flow coefficient phi. I like to state here that the exit flow angles of blade remains almost constant. Here, beta 2 being the exit flow angle of the rotor and alpha 1 be that of the stator. Thus, the summation of tan beta 2 and tan alpha 1 will be invariant. Hence, following the earlier equation, xi would be approximately equal to 1 minus some constant into phi. That is, xi-phi relation would be linear for a wide range of mass flow rate. Further, please note that the static pressure rise may be evaluated from the static temperature rise of the stage if the stage efficiency is known or assessed. Now, the total temperature rise of the stage or the static temperature rise can be evaluated from the specific work input from equation 4 as del T0 is equal to del Ts is equal to Cz into U divided by Cp into tan beta 1 minus tan beta 2, where del T0 be the total temperature and del Ps be the static temperature across the stage. However, the stage temperature rise in the actual case will be less than that of the calculated value from equation 5 owing to the three-dimensional effect in the compressor annulus. This factor has been taken care by introducing lambda, which is called work done factor. This work done factor is a measure of ratio of actual work absorbing capacity of the stage to its ideal value as calculated by equation 5. Here I like to pause stating that the equation 5 has been evaluated following the assumption that the radial distribution of axial velocity is constant within the annulus. However, that relation is not truly valid. That's why I've stated here that the radial distribution of axial velocity is not truly constant across the annulus, but becomes increasingly peaky as the flow proceeds, settling down to a fixed profile at about 4th stage of the compressor. This happens because of growth of boundary layer on the hub and the casing. Thus, in nutshell, a factor lambda will be introduced in equation 5 to take care the effect of three-dimensionality within the annulus. The axial distribution of velocity has been illustrated here. Please note that the boundary layer will grow on the hub and the casing, and thereby the velocity in the annulus would not be constant. So at this first stage, I have indicated a velocity profile from hub to tip, while at stage 4, the velocity profile would be settled at a value where the central region, the value of velocity would be higher than the hub and the casing. This I have illustrated in the earlier slide. Now the work capacity can be stated as, or the specific work input can be expressed as W is equal to U into C theta 2 minus C theta 1, which can be written as U into U minus W theta 2 minus C theta 1 following the velocity triangle, and thus I can write W would be equal to U within the bracket U minus Cz within bracket tan beta 2 plus tan alpha 1, where tan beta 2 would be the exit flow angle from the rotor and tan alpha 1 will be the exit flow angle from the stator. also indicated that exit flow angle from a blade would remain almost constant, that is summation of tan beta 2 plus tan alpha 1 remains invariant for a wide range of flow. Thus, following this equation, an increase of Cz would result in a decrease of work input and vice versa. Thus, the effect of an increase of Cz in the central region of the annulus would reduce the work capacity. This reduction should, however, be compensated by increase of work capacity in the region of tip and hub because of reduction of Cz. Unfortunately, the influence of boundary layer on the hub and the casing and the tip vortex that produced because of tip clearance have an adverse effect on this compensation process, and the net effect is a loss in the total work capacity. Hence, lambda into W is the measure of actual work input to the stage. Thus, the actual stage temperature rise is given by del T0 is equal to del Ts is equal to lambda into Cz into U divided by Cp within bracket tan beta 1 minus tan beta 2. That is equation number 6, where del T0 is the total temperature and del Ts be the static temperature across the stage, and lambda is the work done factor. Furthermore, the variation of work done factor with number of stages has been indicated in the figure below, which illustrates that as number of stages increases, the work done factor decreases, and after a certain number of stages, it would almost saturate. That is, here after 16, the value of work done factor almost remains constant. Thus, the equation 6 will give us the total temperature or static temperature rise of a stage. And after evaluating this stage temperature rise, we can assess the pressure ratio of the stage if efficiency is known. I have derived here the expression of stage pressure ratio. Now the stage pressure rise can be evaluated from the known temperature rise if the isentropic efficiency of the stage eta S is assessed. Let us consider now the stage isentropic efficiency be eta S, and then I can write eta S is equal to isentropic temperature rise divided by actual temperature rise. Now, referring the HS diagram of a stage in a compressor, then eta S can be written as T03S minus T01 divided by T03 minus T01. T03S is the isentropic temperature rise as indicated here. So, eta S can be written as, let me take common T01, from numerator, so it will be equal to T01 into T03S divided by T01 minus 1. Now, ratio of T03S by T01 can be represented as pressure ratio P03 by P01. Thus, eta S can be written as T01 within bracket P03 by P01 to the power gamma minus 1 by gamma minus 1 divided by delta T0. Delta T0 is the temperature rise of the stage. Equation 6 gives the value of delta T0. Thus, from here I can write P03 by P01, which is the pressure ratio of the stage. Thus, P03 by P01 to the power gamma minus 1 by gamma is equal to 1 plus eta is delta T0 divided by T01. T01 is the inlet total temperature at the stage. Hence, the stage pressure ratio can be expressed as P03 by P01 is equal to within bracket 1 plus eta S delta T0 by T01 to the power gamma minus 1 by gamma, where delta T0 is the temperature rise across a stage and T01 is the total temperature of the fluid at entry to a stage. Furthermore, the stage pressure ratio can be determined only if isentropic efficiency of the stage eta S is known to us. Now, if all stages are designed for the same work input, then delta 0 is equal to xi into U squared divided by Cp would be the same for different stages. However, the pressure ratio would be different considering the fact that the stage pressure ratio depends on T01. Thus, we may conclude here that the distribution of temperature across different stages determine the compressor performance. Further, please note here that even if a compressor is designed with identical stages where delta 0 being the same, then pressure rise would be different for different stages. Thus, the questions remains unanswered how to evaluate the overall pressure rise of a compressor. This will be discussed in the next section. Thank you for listening.